So this is the Osmosis one. I'm going to use potato, but you could do it with other vegetables as well. I'm not really going to describe how Osmosis works here. What we're interested in is the practical kind of techniques. So I'm going to use my potato on a white tile. Just for safety, I'm not pushing it into my hand. So I'm going to take out my little potato core. There we go. Now, I want to be taking these from the same potato each time, and the reason is if I keep using different potatoes, I can't be as sure that my results are going to be valid. And this word valid means in an experiment that the only thing that is going to change is my independent variable. That's the only thing I want to be changing, and the independent variable in this experiment, as it turns out, is actually concentration. So I'm going to put my potatoes into different concentrations. For example, I'm going to use 0.0 molar and 1 molar. I'm going to use two concentrations for this, just for the time being. Remember, the capital M for molar is a measure of concentration, and 0.0 and 1.0, they've both got the same number of decimal places, notice. Anyway, I want to keep everything the same if possible, which means I don't want some bits of potato with skin on the end and some not. So I'm going to trim the skin off both ends first of all, keeping my fingers away from the blade. And I'm going to get myself some cylinders, all of equal size. Now I'm going to do this quite quickly, but you can obviously, as long as you know, that properly, and finally just that one centimetre there. So I've made myself some cylinders, all of sort of, it should be equal size. Now they're not quite of equal size, in fact that one's quite a lot bigger. Let's just neat that off. They're not all of equal size, so I've rushed it, but that again is another cause of another source of error. What if my potato cells are not all the same size? Now, as it happens, when we do some of the maths with this, it can get rid of some of those errors for us, but ideally these would all be equal size. Okay, so I've now got everything set up. I'm going to record the mass in grams, and don't put weight here. Weight is a different thing. Weight is a force. Talk to your physics teachers if you're not sure the difference, but it's going to be mass in grams, and I'm going to measure the original mass, and then I'm going to measure the final mass, because these potato cylinders will change in mass as they either gain or lose water by osmosis. My concentration, remember, is my independent variable. The independent variable always goes in that first column. I don't need to write the units because I put the units at the top. So I'm doing 2, I'm doing 0, or pure water actually, and 1.0. So this will be a sugar solution actually. I'm going to use sucrose concentration. Okay. Now notice with my scale, normally, my balance, normally we don't do this, but it reads on here 0, and you might think, okay, that's fine. Do I know that my balance actually works? Because it could be that there's something wrong with it. So I can do something called calibration, and this is a 20 gram mass. So if I know that that mass is 20 grams, and I put it on top of here, does it actually weigh 20 grams? Now, it turns out on here it says, you can read that, 20.09. Now, it could be a problem with my balance. It could be a problem that this isn't exactly 20 grams. In fact, that's probably more likely that maybe it's got picked up some extra, there might be dirt on it, or they might have picked up some extra oxygen possibly and reacted with it. But this idea of checking your equipment, does it actually measure what you think it's going to measure, is called calibration, and it helps to reduce errors. Okay, right, so let's just measure some of our potato cylinders. I'm actually going to put a bit of paper towel on top of here just to keep it just to keep my pan dry. Now when I put that on, notice this has gone up to 0.13 because it's measuring the mass of that paper. Now if I just drop my potato cylinder on there, I've got what's called a 0 error, because it's not at 0 when I started off. So I need to make sure that this is reading 0 before I start. It's another potential source of error. So I'll pop my little potato cylinder on there, and that is 0.61. So that one is going to go into my distilled water, and I'll measure my second one. Oh goodness me, I've now got 0.76. Again, notice I don't need to put my units in because I put them at the top of the table. So that's my original, and that's going to be my final mass. Don't worry about these end columns for the moment. What this is showing me is that I didn't get the same volume with these cylinders. I used the same size borer, so the diameter was the same, but I've obviously made an error when it came to measuring the length. So one of these potato cylinders is potentially a little bit large. It's got a larger volume. It might be that I got it exactly right, but for some reason that one is a bit denser than the other one. I don't know, I can't tell, but I do know the difference. Not going to matter too much for this, because we're going to work out as a percentage change and not just with the raw mass. But that's what I do all the way through this, always thinking the only thing I want to be different is this. The only thing I want to change is this. Anything else that's different is potentially a source of error, and that is going to make things less accurate for me. Accuracy means, is it near the real result? And the more errors I have, the further away it's going to get from that result. So I've now left my cylinders in the different solutions for a certain amount of time and to take them out. So this one has been in the pure water, and it's been in there for 6 hours, and the one that has been in the 1 molar solution, sugar solution, has also been in 6 hours. It's the same time because I need to keep everything the same if I can. Now to dry them off, I've got to also dry them off in the same way. So there's water that's sort of just sitting on the outside of these. So what I'm going to do is, I'm just going to turn it over on one side, just gently give it a little pat. Again, and again. So what I'm doing here is using the same pattern. I've flipped it over 1, 2, 3, 4 times, and I can now maybe give it a little roll, a gentle roll, to get rid of any sort of excess on the outside. Let's roll it down to the end of my paper towel and roll it back up, so I know it's the same distance. Okay, I can then let's just get a bit of paper towel just to stick on here again. Remember, I zero it so I don't have those zero errors, and I would put my cylinder on there, and it's now gone up to, goodness me, 2.52. What a massive change we've got there. So 2.52, and I'll do the same with my one that has been sitting in the 1 molar solution. So what I'll do is, I'm going to use the same technique. I roll it onto its side, and goodness me, you can see this one is much smaller. I roll it that way and up, but you get the idea. I'd roll it the same number of times. That's on 0, and I record the mass of this one. Goodness me, it's lost mass. This is kind of what we expected to see. It's gone down to 0.27, and now I've got my 2 sets of readings. Okay, so let's now do a bit of calculation. We're going to work out percentage change, and the formula for this is the same whenever you do a percentage change. We happen to be doing percent change mass. Could be anything, could be length, you know, we could have done that, but we're going to do mass. Right, I know first of all this has gone up, so it's going to be a positive percentage, and that this one, the final reading, has gone down. It got smaller, it lost mass, it's going to be negative. The formula you would use is the final reading minus the original reading divided by the original reading. Or if you like, F-O-O-L, fool is the way to remember it. We multiply the whole thing by 100 because we want a percentage. And it's worth at this point just having a quick kind of estimate, a rough and ready estimate. So on that one, we've gone from 0.61 to 2.52. Okay, if that increased by 100%, it would be like doubling it. What about if we go up by another 0.6, so that's 200%, that would be 1.8. What if we went up another 0.6, 2.4? Well, that's not far away from that, is it? So we've got up 100, 200, 300%. So it's going to be roughly somewhere around 300%, perhaps a little bit more. Let's have a look. So 2.52 minus our original 0.61, divide it by the original, times it all by 100, 313%. Now, it's fine here to keep it as a rounded number when we do the percentages. You know, I could maybe go to 313.1 if I wanted to. It's not going to hurt me particularly, unless it tells you in the question, but that's fine. I'm not working out a mean here, I'm working out percentage change, and that's fine. I can't really go 313.114 or 115. We've not been that precise in our measurements, really. And the second one, this is a bit harder, but if you think it's gone down, if it went down to half, about 50%, that's not too far away. Smaller numbers here, but you know, somewhere around the 50s maybe. maybe a bit either side. So let's have a look. 0.27 minus 0.76 divided by 0.76 and times 100, 64.5. Yeah, and that looks about right. So now I'm plotting my data. On my x-axis, my independent variable is going to be the concentration. Up the side is going to be the percentage change. We can't go any lower than 100, by the way, because that would imply that it got negative mass. It shriveled up to nothing and kept going. So we're never going to be below 100, but just for our results, it's fine. So at 0, we'd have 313, whatever it is, somewhere up here. And for a 1 molar one, what would be a minus 64.5? So let's say, what should we go up in? 2, 4, 6, 8. Let's say that's 1 molar there. So we'll have about there, right? Now, we've only got 2 sets of data. I'm going to draw a line of best fit. It's quite easy, actually, one to do. So if I said, well, what's the concentration of sugars in my potato? It would be where the line crossed the x-axis. Now, if I wanted to increase the accuracy of this, I would need to have more results between the 1 and the 0. Okay, so I'd do it at more intervals. So, I might get data that actually looks a bit more like this, which might change my line of best fit. I might say, actually, it's there. So by getting more data, I can get a better answer or a more accurate answer, the truthful value, to what my actual number is. So don't fall into this trap of as soon as you see this, a question that says, how do you make it more accurate? Oh, I'll repeat the experiment. If I did repeats, which, good idea to do it, it might make me more confident with my data around a certain point, but it doesn't necessarily make it more accurate. Okay, accuracy is about getting more data, in this case between the intervals, and also making sure that I'm reducing all the errors that we've talked about all the way through. I'm going to keep it for the same amount of time. I'm going to use the same volumes of liquids. I'm going to keep it all at the same temperature. That's what you do to improve on your accuracy.